I was in the MEU came in December 76, and then I went away for a bit to Bristol and to Schlumberger, and then I came back and I was in ComLab, and then ComLab moved to maths, and then I retired at the end of 2016. So I was going to talk a little bit about some work Brian did before I started, because basically there's nobody else here to say about this. Let's see, does this work? It's easier if I do this. So I was going to talk first of all about his, what I knew about him, because I was doing my PhD in Cambridge when he advertised a job and I came here. And one of the things he'd done is his PhD work, which you can see it's submitted in 1964 and his PhD is dated 1965. But it was to develop a device to measure shear on a plate. It's quite a difficult problem because the way people try to measure velocity is normally with a probe. So you've got to put something into the fluid, and as soon as you put something into the fluid, you change what the fluid's doing. And then if you're trying to measure the shear, which is the rate of change of the velocity near a wall, say, then the probe, as it gets nearer the wall, will have an even bigger effect on the flow. So it becomes much, much more difficult to calibrate these sorts of devices. So Brian, working with Don Schultz, developed these devices, and this is the sort of things. They're thin films, and the idea is you put a current through them, and then if fluid flows past them, the temperature will change and the current will slightly change. And so you can measure changes in temperature, and then you can appeal to an analogue of temperature related to shear to try and back out what the shear is. So these were the devices that Brian had developed in his PhD, and later on I'll show you some that we used when I was there. Then I am going to tell the next bit, which is I don't quite know how Brian came to be interested in it, but he became interested in heart valves. And this is in your heart is a tricuspid valve, and this thing works. So this has been excised and opened out. So you've got to imagine, where are we? Is that the bit? Yeah. That bit there is actually attached to that bit there. So it wraps around, and there are 3 sinuses, and then there are 3 membranes, and their function is to stop blood coming back in when the ventricle. So the ventricle squeezes closed, pushes the blood out, and then as it opens out, you don't want blood coming back from the aorta, you want the blood to come from another part of the heart. And this was something that so Brian in his paper, which I'll talk about in a moment, says, Leonardo knew the physiology, knew the sort of structure of the heart, but nobody knew why or how these valves really worked. And Brian came up with an explanation. I don't know how he came up with it, but he and Francis published in Nature in 1968 a theory that what happened when these heart valves opened was there was a vortex formed behind them, and that vortex would play a role in closing the heart valves. And he then went on to, with, I think Larry, I'm not sure, I think it's Larry Talbot. With Talbot, they actually tried to understand a bit more what was going on. And you can see they've done some experiments in the water tunnel. It looks like a simple experiment when you see a picture of it, but in fact, I think there are some quite difficult technical aspects of taking films of flow in a tube when you're looking at the side of the tube. And they also tried to do some modelling of it, exactly as Lionel was talking about. And this was the sort of thing they're trying to do. So this is the picture looking end on. The sinuses are there, and then these cusps, the little leaflets that are going to close around there. And Brian's theory was that as the valve opened, this vortex would form, and it would then play a role in the closure. And the experiment they did was to build a tunnel with a flow coming along. So it's going to be a pulsatile flow coming along. They put a velocity probe in so we can measure when the flow's coming forward and when it's going backwards. And then they have a cine camera. And I say taking this cine of that tube is a non-trivial thing as far as I can see. But they managed it, and these are some pictures from one of their paper, or from the JFM paper. The probe is this bit sticking up there. So that's a little piece sticking up, pointing into the stream, so you can measure the pressure, and from the pressure you infer the velocity. And the valves are closed, and then the ventricle would, if it was a ventricle, the ventricle would start to pump, and the valves start to open. They open very rapidly, and the fluid is all whooshing through, coming out. And then the second part is the rate at which fluid's coming out starts to decrease, and the fluid is still coming through, and then this bit happens. So we're still pushing fluid through the ventricle, but these valves have started to close. And this is incredibly important because if you're trying to create a valve, the last thing you want is to spend a lot of effort pushing fluid through, and then in order to stop the fluid coming back, there's a time delay, and so some fluid comes back into the whatever you're pushing from. So the idea that this valve closed by itself, because of the fluid mechanics that's going on, seems to me really important. And I'm going to make a sort of statement that you can all disagree with, but we're going to hear a lot about Brian's engineering achievements, but I think this is his most important scientific achievement. This solved something that people did not understand, and it's now we know so much more about the heart. People can make artificial valves. We spent ages in the lab, or I didn't, but the lab, MEU spent ages making artificial heart valves. There are lots of options doctors now have, but one of the things they can do is they can try and understand whether the heart valves are functioning properly, because they understand now more about the fluid mechanics. So that was the sort of person that I knew about through the literature when I was in Cambridge. And somehow, after the heart valve work, Brian became interested in membrane oxygenation. And so the difficulty you have is that if you do open heart surgery, you take the chest cavity open, and of course the lungs work because the diaphragm is pumping against the chest cavity. So cavity open, lungs have stopped working. So the very early operations, this is my understanding, the very early operations used a bubble oxygenator. So they took some blood from the person, they would bubble oxygen through the blood, and then return the blood, the oxygen having gone into the blood and carbon dioxide coming out. Now, the problem with this is that this process starts to trigger coagulation of the blood. So the early heart operations had a very short time. The surgeon had to operate in my understanding again is it's like half an hour at most. So that meant that if you could have a device where you did not trigger clotting of blood, then you would have more time. And so this is a membrane oxygenator. And the idea is you have two sheets of membrane, the blood will be between the membranes, gas will be on the other side, oxygen will go through the membrane's porous enough to let gases through, oxygen will go through the membrane, carbon dioxide will come out. Now the fundamental problem you have is diffusion. If you're relying on diffusion to carry out mass transfer, it's very slow in liquids. In gases, if a bit of gas goes off here, you'll hear it all around this room quite quickly. But if it's a fluid, it's a totally different matter. Diffusion rates in fluids are like 10 to the minus 9 meters squared per second. And so that means if you took, say, a channel that was a millimeter wide, it's roughly 1,000 seconds just for something to diffuse across that channel. So diffusion alone is not enough. Now, if you're a chemical engineer, and something doesn't diffuse very well, you take the strategy of let's beat the stuff to death and stir it up as hard as we can. So you mix it as fast as you can. Now, that's great for a lot of chemical processes, but with blood, you'll damage the product, as it were, because it has various formed elements in it. So using the normal chemical engineering solution of turbulent flow to try and mix the gases in the blood doesn't work. And so you need a laminar flow process. And so Brian must have spent a lot of time at the beach, because one of the stories he told me was that he was watching waves come over. You know how you get ripples on the sand? And he was watching the sort of waves wash over these ripples when he had the idea of this device. And it's called, this I think is 1973, this paper. And the idea was to take some metal, fairly thin metal, bend it into a sort of wavy structure, where is it? There, this structure, and then you put a membrane over it, you pressurize the membrane slightly, and you form little, like rivulets on the beach, and then as the blood goes through, you will get vortices, and the vortices will mix the fluid somehow. And that's a picture of the device. Now, this also had a very interesting pumping system that, as far as I know, has never been reused other than once afterwards. But essentially, the device was the sort of thing that, if you've ever been in the MEU in those years, all the machines looked more or less like this. There was a sort of series of plates held together with various perspex and bolts, and then blood would go through them, and in this case, gases come in, and the gases come onto the top, and then they go through into the blood. So that's where I came in, and Brian had a grant, and a guy called Jit Agrawal had been looking. So you must understand at this stage, we knew very, very little about separation from fluid mechanics. It was so difficult. There was no theoretical way of really attacking it very easily. And unsteady separation was just, miles away. So we had so little knowledge of what to expect. And Brian wanted to understand why this thing worked, because if you understood how it worked, you could make it work the way you could tune it in a sense. So Jit had been going to do some experiments where they were going to put some, I think it was a cyanide into some fluid, and then take some pictures of this under some sort of big darkened tent. So I turned up having done theoretical fluid mechanics, and that was not for me. So I had to do much more simple things. So I turned up at the MEU in about December, and I think, now I do apologise if I've got anyone's name wrong, or I've forgotten anyone. I have trouble remembering what I did yesterday most of the time. But so Brian was the boss. Bill Hayworth was, and I've put title Senior RA. I'm not exactly sure what Bill's title was. Elizabeth was there. I was there. Later we were joined by Kira Stefanoff, who worked with me. I'll show you some of her work. John Stearman, who finished just after I left. Now, I can't remember whether it was Rod or Rodney Hill. Does anyone remember? Roger. I wanted to say Roger, and I was worried I was going to get it wrong. So they were DPhil students who I remembered. Martin Jeffrey came and did a lot of animal experiments. Martin was a surgeon who could take a knife to any of us, but would be in endless trouble if he was not careful with taking a knife to a sheep. He was a brilliant and wonderful guy to work with. Francis was the senior technical, and I put senior technical support. Francis essentially knew everything about engineering. And in fact, I think I learnt more about engineering workshop stuff from Francis than I would have from anybody else. And whilst we had brilliant technicians, I'll also tell you a story that Francis told me. I was drawing up some stuff and how I wanted it made. And he said, well, the first time you give it to the technicians, they'll make what they want to make. The second time, they'll make what they think you want. The third time, you'll actually get what you really want. And, we had the most wonderful technical support. Roger, Gerald, later Marcus joined, working with some of the things I did. Jane Randall was the secretary, and Mrs. Collins, Betty, was made the tea. And I'm sure there are graduate and past students. Ranjit Watson, have I gotten the name right, was there. But I've lost track of others. But anyway, that was the unit I joined, quite a small unit, but as Lana said, every week we met and had Brian made meticulous notes of everything we said. In fact, I often wondered what happened to all his notebooks. There must have been thousands of them. But anyway, so this is from my lab book in 1977, and this is the state we're at. We had so little knowledge of what to do that I was going to make up a tunnel, a little water tunnel, that would have some hollows that would be symmetric, they'd have different depths, and some hollows that had a flat wall opposite them, and try and understand something about the fluid mechanics of what's going on. And this is the sort of rig. Now, this is actually my rig in Bristol, but the one in Oxford was a slightly better version of this. But essentially, we had a slide projector where you put a slide in with a slit, and then you reverse the lens. So you turn the lens around, and then you get a little sheet of light that shines through. You have a camera that you take a picture of. You put some particles in it that you hope are more or less neutrally buoyant. You have a motor up here that's pumping, and a pump chamber. And then we can look at what happens when you take these sorts of channels and you pulse them. Now, one of the things that I talked with Lytle about was the fact that these all have the square, the very sharp corners, and he said, don't worry about that, just use a sinusoidal wall. And so we tried to look at effectively sinusoidal furrows. And Brian managed to get a grant, and we bought a PDP-11 computer. And I'm sure every generation thinks that the subsequent generations have it pretty easy, but we had, this PDP had 28 kilobytes of memory. It actually had 32, but we could only address 28. We had analog to digital inputs for it. We had 16 of those, and we had 2 digital to analog. And they turned out to be quite useful because we had a tectonic storage oscilloscope, and we had a Polaroid camera. So I could do some calculations in my 28 kilobytes of memory, display it on the tectonics oscilloscope, storage oscilloscope, take a picture, and then pull it out. So what we really had was, as I described, we had a monitor at 1 frame every half hour. And these are the sorts of things we'd get, and then what I'd have to do is I'd trace over these to get flow patterns, and you can see, you can make up text and all sorts of things if you're willing to go into sort of assembly language and things. So that was the sort of situation where we had this lab, we were doing fluid mechanic experiments, and I was trying to do calculations of what would happen. And so these are some pictures of flow through a channel. So you've got to imagine there's another half the channel you can't see, the opposite side. It's sort of symmetric about the horizontal axis. And then there's a whole series of these, and so it's periodic. And this thing, RE, is a Reynolds number. It's a parameter we use, but essentially it's the speed of the flow. So the higher the Reynolds number, the faster the flow is being pushed through. And if you take very low Reynolds number flows, you just go through and it just follows the channel. And then as you increase the Reynolds number, you get this reverse flow. And this is the vortex, and this is separation, and this is the thing that we can't predict very easily at a theoretical level. And as you increase it, it gets bigger and stronger, and then eventually even this vortex can separate, and you get another vortex behind there. So on the whole, nature doesn't like long, thin vortices. It breaks them up into smaller vortices. So that was some calculations from probably about 1978, 79, and then that was steady flow. And then if we took unsteady flow, this is what happened. And this turns out to be half of the key to why the membrane oxygenator works so well. So as the flow starts up, now time has been scaled so that T is a half is one piston going that way and another half to come back. So T is 1, it goes forward and it comes back. So it starts up and T is 0.1, it's just starting to get speed. Here it's going flat out, maximum speed, and then it starts to slow down. And between these two, I spent months refusing to believe what my calculations were telling me. Because what I was expecting it would, as it speeds up, it would go through there, it would go to there, it would hit go there, and then when it hit Reynolds number 75, it would look like that. And then when the flow decreased, the Reynolds number would decrease, and it would do this. It would go back down through that cascade. That was what I expected. And it didn't. This happened. The vortex became larger. Now, if you've been remembering what I said about the heart valve, you might, at the end of this, think, well, perhaps he should have put 2 and 2 together a bit earlier. But nevertheless, it took a long time for me to believe that that was what was happening. That when the flow slows down, the velocity of the flow remains quite high. It's just the gap gets smaller, so the actual flow rate decreases. And then when the pistons reach the end, what you have is a vortex spinning in the hollow. And then when the flow reverses, that vortex gets pushed out into the middle, and the flow goes round it. It has to, because continuity says the flow's going from right to left there, and I'm going to start making the flow go right to left. So any fluid that comes in through this bit goes around that way. And it pushes it into the middle, and then it reestablishes the vortex, and that's the cycle that goes on. And then Kira took some pictures. Well, we had some other pictures. We had some cine things, but they're not very accurate. But Kira took some wonderful pictures. So these are from Kira and Kira Stefanoff, and they show the vortex slowing down, the vortex growing, and then when the flow's almost come to rest, you have these 2 vortices sitting around there, and then when you take the 2 vortices sitting around there, the flow, they gradually get eroded away. They're being eroded away. And then at this stage, it's going to separate in this bit, and the flow is going back around there. So these things really work. And then by this stage, we had a digital plotter, I should add. We had this nice Hewlett-Packard plotter that I could connect up. So I was able to do things like work out, well, where were all the particles of fluid going during this process? And this is really the first part of the key to how these devices work was that the vortex expands. The second part is what happens in this picture. So it took a bunch of particles in here, thousands of particles, and you track them all simultaneously. And as the flow pushes right to left, they get pushed down the middle. Some of them get entrained into this vortex there. But that's not the key to what happens. The key is between that slide and that slide. Because what has happened is as the flow starts to go back, there's a vortex smack in the middle of the channel. So any fluid that's in the middle of the channel cannot go back down the middle. It has to go to the sides. So between those 2, we physically move fluid the width of the channel. And that's thousands and thousands of times more powerful than just diffusion. And that's why these devices work so well. Because we've now taken fluid from the center, we've pushed it into the side, it's now up against the wall. And so the problems we have with diffusion at the boundary of the channel go away because we're stirring it up, but we're stirring it in a way that is very sympathetic to the fact that there are particles in there. So that was the device, that was Kira's, I said about hot film probes. So Kira painted all these little hot film probes in different places and did a whole lot of experiments. And then the shimmy, the membrane in channels was very difficult to make. So what Brian developed and overcame a lot of technical problems in dealing with this was a dimpled membrane. So it's a bit more like the surface of a golf ball. So these are all little dimples. And in each dimple, you're going to get a little vortex, and the little vortex is going to expand, and it's going to have the same sort of dynamics. But this membrane is easier to manufacture, easier to configure in the channel. The problem if you have, well, in fact, we had problems with this one as well, but if you, say, have 3 or 4 channels, and one channel is a bit thinner than the others, all the fluid will go down the thicker channels and not down the thinner ones. So you might think you've got 3, 4, or 5 channels functioning, but in fact some of them are not working very well. So it was used for, the oxygenator turned into dialysis, so Martin Jeffrey spent a lot of time looking at dialysis with sheep. And dialysis is another example of where engineering and medicine have to be a little careful because, again, this is my understanding of our conclusion. If you took a person is ill, they need dialysis, they have an elevated level of urea and creatinine. If you totally take out all the urea and creatinine from their blood. So you do a perfect job of washing it, and you put it back into the body. They get a sort of shock because of this, the gradient between the blood that they're returning, the concentrations in the blood that you're returning, and the concentration in the blood that's in the body. So, you know, just building a perfect machine is sometimes not the only, not the right answer for some medical problems. So have I got a couple of minutes on? Yeah. So after that, I went to Bristol, and at Bristol, I discovered something called a vortex wave. I did this by accident, having heard my supervisor at Cambridge was interested in the crop cough sounds. I don't know if when you have your pressure taken, essentially you take an artery and you collapse it, and no flow, no sound. And then when they release the sound, the pressure, as it first enables fluid to come through, you start to get a sound. So when you first hear the sound, it's the highest pressure, so that's systolic pressure. And then when you hear no sound, you've hit diastolic pressure. It's pretty crude in some ways, but that's essentially the crop cough sound. So Tim Pedley in Cambridge had an experiment where they took a channel with a wall that they could oscillate the wall. So he had the wall oscillating up and down with steady flow going through it, and he discovered a train of vortices would happen. We're going to give you the crop cough sounds. So my deduction on was that, well, if I took a fixed wall, but I oscillated the flow, I should get the same thing. And this is an example of what you get. This is an unsteady sequence. So it's peak flow, and there's a channel that has a step. Behind there is a step. So the channel starts at one side, and then it doubles in width. And so you get this vortex, but as it slows down, you get this wave of vortices that go on. And that was what we proposed for a vortex wave device, where we would make up a ladder that had rungs. Where are we? So there'd be a rung there on one side, and then it'd be offset on the other side. So we would have this. This is from Brian and I patented this. This is from that patent. And then these are the sorts of flows you got inside that. And it worked. And it did work. And Hugh Millward did a lot of work on it, and you can get some very interesting effects. But I was going to stop there, because I think the main thing I wanted to talk about was things Brian had done before I came, and I really do believe that his work on heart valves will be, you know, all the engineering stuff is fantastically brilliant, and he was a wonderful engineer, but that work on heart valves is something very special. And then all this other stuff. And I, you know, have a career that started in the lab, and I've been eternally grateful. So I'll stop there.